Hi guys, I hope you're having a wonderful day. Let's talk about stoichiometry and heat calculations. So with stoichiometry, when it comes to calculating the heat transferred in a reaction, usually you are given a reaction with a certain delta H in kilojoules per mole of reaction as written, and you're asked how much heat is released when you use a certain amount, or you are given a certain amount and asked how much heat is transferred. So let's look at an example here. It says when iron reacts with oxygen, it forms Fe2O3 and releases 825 kilojoules per mole of reaction. How many kilojoules of heat are evolved when 27.9 grams of iron are reacted with an excess of oxygen? So it's talking about a chemical reaction, so the first thing we want to do is write it out. So Fe plus O2 yields Fe2O3. Let's balance it. So we need 3 O2s and 2 Fe2O3 and then 4 Fes. They tell us that the delta H for this reaction is 825 kilojoules per mole of reaction. And it actually says releases, so it's actually negative 825 kilojoules per mole of reaction. So what does that mean? What does that per mole of reaction means? That means that it's for the reaction as written. So that's for 4 moles of iron, or 3 moles of oxygen, or 2 moles of Fe2O3. Whether it says, if it's written like this and it says kilojoules per mole or of mole of reaction, that's what it means. So the question is, how much heat is evolved when 27.9 grams of iron react? So this amount of heat is released when 4 moles of iron react. So we want to know just for 27.9 grams how much would be released. So you'd start with the 27.9 grams of Fe, change that to moles. Molar mass is 55.85. So your grams cancel, we're now at moles. And then we're going to put moles on the bottom because we want that to cancel. And we're going to put kilojoules on top because that's what we're solving for, is the heat in kilojoules. So we know that there's negative 825 kilojoules, and that is for 4 moles of iron. So the answer is, you can either say negative 103 kilojoules, or you can say 103 kilojoules evolved or released. So as always, either put a negative, meaning it's released, or write it as positive and then write the word released or evolved. So it's really important to distinguish between this delta H versus this delta H. They're both delta H's, they're both for the same reaction, but this is for a certain amount that we're using, the 27.9 grams. This is for the reaction as written. So I want you to take a look at this box here. So it says it's very important to distinguish if heat is for the certain quantity given, like in joules or kilojoules, like here, that was for a certain number of grams, or if it's per mole, or for the balanced reaction, kilojoules per mole. So if you are calculating the enthalpy using any standard data table, it's usually in kilojoules per mole of reaction, or just kilojoules per mole. If I look up any number, so if it's in a table, or they write a reaction and then delta H next to it, that means it's kilojoules per mole, usually of reaction. If you are calculating the enthalpy using a set amount of grams, like we did here, in an experiment, also this is true for like Q equals MC delta T or Q equals ML. Those were for certain masses, right? Certain number of grams, because we put the M in there. That means that your answer is going to be in joules or kilojoules, not per mole. So if you want it per mole, what you do is you can then convert it to kilojoules per mole by dividing by the moles, usually of the reactant. So if you're doing Q equals MC delta T, or Q equals ML, or calorimetry, like where delta H of a reaction is equal to negative Q of surroundings or whatever, which is MC delta T here, then you're going to get joules or kilojoules. Or you're using a certain number of grams somehow, it's going to be in joules or kilojoules. If it's from a table, or you see a reaction and then a delta H written next to it, or it tells you kilojoules per mole of reaction, then that means it's per mole. Okay? All right, let's look at the next problem here. It says, if 42.8 grams of methane is burned on a cake of ice at 0 Celsius, how many grams of ice would it melt? The heat of combustion of methane is negative 890 kilojoules per mole. So first, let's think about what's happening here. So I have this cake of ice, they say. This is the ice. And I'm taking some methane, the CH4, and I'm burning it. So adding oxygen to it, burning it. It's an exothermic reaction. It's going to give off heat. They tell me the heat of the reaction is negative 890 kilojoules per mole. The negative is because it's exothermic. And so as it releases heat, some of the ice will melt. So the question is, if all the heat is transferred to the ice, how many grams of ice would melt? The first thing I'm going to say is I'm going to write down the reaction here. So CH4 is methane. It's burning, so I add oxygen to it. I get CO2 and H2O. And to balance it, we need a 2 here, 2 there. Delta H for this reaction, they tell us, is negative 890 kilojoules per mole. Now, this is, again, per mole of reaction, right? Because it says heat of combustion is per kilojoules per mole. So, I don't have a mole of methane. This is for 1 mole of methane, right? I have 42.8 grams. So I'm going to go ahead and change that delta H so that it's for the 42.8 grams. So 42.8 grams of CH4. I'll convert that to moles first. 1 mole of methane is 16 grams. And then I'm going to say negative 890 kilojoules for, in this case, just 1 mole, because the coefficient here is 1, for 1 mole of methane. So that cancels, and I get negative 2,380 kilojoules. Okay, this is how much is released for the 42.8 grams of methane. That's how much heat is transferred to my ice. So now I can say Q of the ice is equal to negative delta H of the reaction, right? One is my system, one is my surroundings. It doesn't matter which one you write it, so you can write delta H of the reaction is equal to negative Q of ice, same thing. So my Q of ice is equal to negative, my delta H of reaction was negative 2,380 kilojoules. So this part up here, where we figured this out, that is stoic, right? That's what we just did. But this part right here is calorimetry and actually change in state, right? Because once I figure out that this is positive 2,380 kilojoules, this is the Q of ice, and it's asking me, it's telling me that the ice is at 0 and it's going to melt. So that's actually a phase change, not an MC delta T. So normally, you know, if it was water, the temperature would rise or something like that, I'd do an MC delta T. In this case, I'm doing a Q equals ML because I'm melting the ice. So Q of ice, we know, is this number. We also know that Q of ice is equal to ML. And in this case, the latent heat of fusion, right? So positive 2,380. I'm going to do it in joules. because Q equals ml will give you the number in joules, not in kilojoules. This is equal to the M, which is what I'm looking for, the mass of the ice, times the latent heat of fusion, which if they give you this question, they'd give it to you in the question, but since this is part of our notes, or if it's in our homework, you can look it up. The latent heat of fusion for water is 334 joules per gram, or I can't remember if it's 334 or 333, depending on how you round it. And you solve for the mass of the ice, and it ends up being 144 grams of ice melt. Isn't that neat? So we kind of combined stoichiometry with calorimetry with state change. That's pretty cool.